Hi everyone, this is Mohamad Mokbel, and today I'll be talking about an exploratory endeavor in the reverse engineering of a multi-platform compiler. So this is an exploratory endeavor, meaning that it is not set in stone. So I took left and right in order to get what I want out of this particular research project. And I touched on a lot of things during this process instead of focusing on one particular thing. So thus the name Exploratory. And in particular, in this talk, I'll be talking about the PureBasic compiler, which you've probably never heard of. And my first encounter with this compiler was back in 2015 when I reverse engineered malware, but I didn't pay much attention to it at that time until Teaser in November 2019 published a blog post about a ransomware called PureLocker, which is written in the PureBasic language. And thus, that was the trigger to work on this compiler again and do this research. So without further ado, let me start the presentation. So who am I? I'm a senior security researcher at Trend Micro. I work for the Digital Vaccine Lab, and my interests lie in the area of reverse engineering, malware research, intrusion detection systems, intrusion prevention systems, C++, compilers and software performance analysis. And in particular, I have a fond interest of exotic communication protocols, especially protocols that do not adhere to these specifications. Introduction. So first, just to recap, you're probably familiar with the process of compilation and how complicated it can get, especially when you want to compile a native language. So it could go through multiple phases and processes, and there are lots of libraries involved in the compilation process, and you have different levels of optimizations and different file formats such as COF file format, dwarf file format, and also you have the code generation aspect, the object file that's being generated, and among other things such as OS dependencies. And for malware, they are mostly written in native languages. And in particular, like statistically speaking, they're written in either x86 assembly language, 32 or 64-bit, and then you have C, C++, Objective-C, and Delphi. And each of these languages, they have different runtime libraries. Now, of interest is when these binaries are compiled statically, and it becomes harder to identify referenced libraries in the binary. Why this is an issue is because when you want to reverse engineer a binary, be it a malware or any other binary, when I want to use, for example, IDA, you would rather focus on the code that is relevant to you instead of having to go through code that is a library specific. So if you can filter out the noise and focus on the actual code that is written by the author instead of reversing the library's code, it's much better. And just note that reversing native code is much harder than reversing code that is interpreted or has any form of intermediate language, such as .NET or Java. And those could be decompiled easily. So yeah. And for just like to give an example about the emergence of new programming languages that generate native code, and especially when it comes to the reverse engineering of those languages. We have the Go language by Google. So when this first came out and malware authors started using it, the reversing of this language needed a new research. And of particular, there are two researchers who worked on coming up with tools to help reverse engineer reversing Go binaries. You have Tim Strazzari, who did the initial work on this language, and which culminated in the release of a Go loader plugin for IDA. That was good. And then comes Juan Calvé from PNF Software, and he did a very, very good work on reversing Go binaries, which culminated in the release of multiple Python scripts, but it is specific to a PNF software, a GPD compiler. But it's extremely well done research. Now, why they are able to provide lots of information for Go binaries is because of the language itself, the way it gets the way it gets compiled. It is statically linked. There are no external dependencies, and however, it stores Go-specific metadata. It's this metadata that allows the recovery of some of the function information relevant for reverse engineering. And Go is a multi-platform language, thus the favorite language for malware authors to use. So the thought layout will be as follows. So first we'll introduce PureBasic language, the language itself, and go through a particular example. And then we'll talk about the compilers and the libraries. And then we'll introduce the thesis of the talk, which is, like the whole purpose of this talk is that at the end of the day, we want to help reverse engineers reversing PureBasic language, whether you're reversing a malware or another application written in this language. And so this language has its own proprietary file format, which requires understanding this particular structure and reversing it so that we can extract those libraries in their original form so that we can use them later on with IDA so that it helps us in reversing those binaries. And after that, we will go through 2 case studies just to highlight how we can use IDA FLIRT signatures to help your reverse engineer PureBasic binaries. So PureBasic, the language, it produces native code for Windows, macOS, and Linux platform. It's extremely powerful. Again, remember, it produces native code, so just like C++ compilers, and it has extensive library support. If you want to use audio, you want to write a game, 2D, 3D, you want to write a database code, networking, even parsing, regex, memory stuff, compression, if you want to write a GUI application, and whatever. It's a very high-level language, actually. It has a syntax similar to the basic language, and of interest in this language is that it has actually support for inline assembly for both 32 and 64-bit architectures. Surprisingly, like even Visual Studio Compiler doesn't come with inline assembly support for the 64-bit architecture. And for assembler, it uses the FASM assembler, the open source FASM assembler on Windows and Linux, whereas for OS X, it uses the YASM assembler. And yes, despite it being a very high-level language, it does provide actually access to pointers with a memory access. Also, it provides support for calling into OS native shared libraries functions. And to do so, you can invoke either of those 2 functions, call function or call C function, depending on the calling convention. So you're not left out just to use the actual PureBasic compiler supported APIs. And of course, it goes without saying that this language has support for procedures, meaning functions, structures, interfaces, which are known as classes in other languages, and also supports basic inheritance. There's just one level inheritance. And in this language, you can use inheritance via the extends keyword. So this is a code that shows how to use PureBasic language. It's a very simple and very structured. So in this particular example, we have a structure named COVID-19, and it has these data members. So first you have the name followed by dot, followed by the type. and it's just a one word to identify the type. For example, the name member gets the string type. Dead has the Boolean type. A data infected string, age, integer type. And we want to create a list of this particular type that is COVID-19. So you use the new list keyword with the name patients of type COVID-19, and then followed by add elements, call, so that we can push this new list, this element to the list called patients. Now we want to populate each of these members of the structure, and the way to do so is via first the name of the element, followed by the data member, followed by the value, and this is how you populate it according to this very specific structure. And if you're tired of repeating the name of the list, what you can do is use the keyword with followed by the list name, the structure name, whatever you want to call it, and then end with, and then you list in between the data members with their values. And if you want to select a particular element in this list, first you specify the list name followed by the index. In this case, we only have one element, so it is 0. And this is followed by the API called message requester. And this is literally just a message box on Windows. It's responsible for displaying a message with the title being the number of elements in this list. And the body of the message is the name of the patient. And we have the constant that shows the button OK in the message. And afterwards, we clear the structure. So just to give you an idea of what library is being referenced when calling these functions, it is as follows. So for clear structure, this is a reference from the memory library. For linked list library, you have these 3 functions: a new list, add element, and select element. And for the message requester API, this is referenced inside the requester library. So after executing this particular code, you get this message box, just what you would expect. It's quite simple. So PureBasic compilation components. Here we'll be talking about most of the files that reside inside the compilers directory. Like when you install PureBasic, and by the way, PureBasic is a commercial compiler. It's not expensive, but it's a commercial one, so it's not open source. Thus, this research. So inside the compiler directory, you will find the FASM.exe executable, which is an open source flat assembler for x86 processors. It produces both 32 and 64-bit code. And what's interesting about this assembly is that it has support for what's known as macro instruction language. And it makes it easier to write assembly language. And this assembler is responsible for producing the actual object file. And it is in COF format, Common Object File format. So this is the assembly that is used by this compiler. For linking, PureBasic compiler uses actually a linker by Payload, and this is responsible for linking the multiple object files should your project references multiple PureBasic compilation units. And polink is an open source, another open source linker. Polib, this is a library manager, and it's used for building import libraries, extracting object files from a given library. You can list the object file, you can delete it from the library and whatnot. And actually, at one point in time, I was planning to implement this particular functionality myself until I stumbled on this particular executable that's shipped by the compiler itself. And then you have the polink.exe, which is also another open source resource compiler by Payload. And this is responsible for creating the resource files. Now, the most important executable is the PB compiler. So this is the orchestrator. This is the one that leads to the generation of the final executable by linking all of those prior executables that I talked about. And it is responsible for emitting the actual x86, 32-bit, and 64-bit FASM assembly instructions into the PureBasic.asm file. So every time you compile a PureBasic file, it's always assembled under this particular file, PureBasic.asm. Yeah. So this is the most important executable. So as you can tell, the author is actually quite smart. He used all of these open source libraries to do most of the back end work when writing a compiler, instead of having to implement a linker and an assembler and most of the other tools like by himself or herself. So he only has to do the actual front end type work, but not exactly solely for front end, but the majority of the work done by the author is enough so that he can leverage other people work and generate the final executable file. This slide highlights the compilation phases when compiling a PureBasic source code translation unit. So we'll take this as an example, which only consists of this API message requester with the title hello and the body world and the flag message requester OK, which is just a button with the OK message. And this is saved under the name example.pb, which is the extension of PureBasic files. So first you load it inside the IDE, or you compile it from the command line. So what pb compile.exe does at this point is it's responsible for doing the lexical, syntax, and code generation steps. So after it produces the PureBasic.asm file, as shown in this assembly code snippet, which is heavily truncated, it is quite simple, and I believe it's self-explanatory to read as well. There's nothing unique about it. Then comes the calling of the FASM assembler, which takes the assembly file generated and introduces the object file purebasic.obj. And afterwards, you have the linker, which takes the object file and generates a purebasic.exe file. And the process, I believe, is straightforward. So just to give you an example of what happens like at runtime, or what options used by the compiler when compiling a given PureBasic file. And like this is literally the options used, like for this particular example. So the orchestrator, the pb-compiler.exe, invokes the linker with these arguments. So here's specifying that the forces multiple object files, and the file has to be saved under this name. And the answer is PureBasic start. So if you go back to the previous line and look at the assembly code, you will see that the entry, meaning the main function in all languages, has this particular name, PureBasic start, and the subsystem is compiling on Windows, not Linux or OS X, and it's requested not to use any default libraries, and of course it sets the path to the compiler's directory that references all the other relevant libraries and resource libraries. Now, this is probably the start of the most important part of the talk. And as I mentioned at the beginning, or I hope you've read the abstract and the description, PureBasic libraries, they are stored in proprietary file format. Like this is the core of the functionality of the compiler. It is shipped in separate libraries that you can use when compiling your programs, and those are stored in proprietary file format. On Windows, they are stored zlib compressed, of course, in proprietary file format, whereas on macOS and Linux, they are stored encrypted. Of course, we'll go later on in depth of the structure of this proprietary file format and how to extract those libraries in their original format. If we go back to the compilers directory, you'll see multiple libraries. So for example, inside the compilers directory, you see these 12 libraries: debugger.lib, libmariadb.lib, object manager, and the list goes on. For example, when you want to debug your PureBasic file, so the compiler will reference this particular library, debugger.lib. Just to note here, those libraries, they are stored in their actually COF format, so they are not proprietary stored. So it is this directory where the those libraries are stored in a proprietary file formats. And for example, if you want to write a GUI, there will be a library for it. If you want to reference an image, if you want to write HTTP client, FTP client, any of those stuff. And you've got around 116 libraries. Now for Windows, of course, if you recall, I said that you can call into into your OS APIs via the call function called C function, right? And those are stored inside the Windows libraries directory. Those are proxies into the actual Windows libraries. These aren't stored like in proprietary file format. And then, since the compiler comes with its own SDK to write your own library, this is where you store those libraries in this particular directory called user libraries. And another interesting decision by the compiler is what's known as subsystems. So if you want to write code that references OpenGL or DirectX 11 frameworks, which both resides under these two unique libraries, Screen and Sprite, but different architectures, of course, or different code. So there is an abstract code for that, or I should say abstract set of functions that allows you to call into each of those libraries. So instead of using a function specific to OpenGL or another function specific to DirectX 11, there is only one function that calls into both of them. And at the time of compilation, how you specify which subsystem do you want, just via the like a compiler option. And this is actually a smart decision by the author. So this is on Windows. Now for on Linux, the other subsystems, they are GTK2 and Qt. Another good decision by the author of this compiler is what's known as residence file. So these, we're probably familiar with header files for C++ or any other high-level language. But in this case, the author has different file formats for those. And they are called resident files, such as expa.res, opengl.res, purebasic.res. Those are stored in binary format, so they are not in text format like your typical header file. And they are precompiled binaries, and they are only loaded at like when you start the compiler. And they contain predefined structures, interfaces, classes, macros, and constants. Or of course, you can create your own resident files. And this is actually a very smart move because it makes it easier to reference those defined structures and whatnot, and faster as well at the same time. Now, as I mentioned earlier, especially if you go back to this slide, and of particular is the pure libraries directory and the subsystems directory. Those libraries contains most of the like the crust of the functionality of the compiler whenever you want to use any of these libraries. And it's those that are stored in proprietary file format. So the whole purpose of doing this research is that we can extract those libraries in their original format and then generate either FLIRT signatures and then use them to annotate our own PureBasic binary, so that we don't have to waste time reversing stuff that we already know about. So when compiling a PP program, the compiler actually extracts dynamically all these libraries in their original format, and these are stored inside, like under the current user's temporary directory under this particular name, PureBasic followed by get account ID value, just a digit. And it looks like as follows. Like you have the get account directory followed by the library name.lib. So you can actually go into this directory after compiling your program and get those libraries in their proprietary file format. And additionally, in this very same directory, you can find also the object file being created, as well as the other resource and resident files. What you need to keep in mind is that this folder and everything written inside it is transient, and it gets deleted right after compilation is complete. Thus, every time you want to get access to those libraries, or every other library, you're going to have to compile a program that references a code from that particular library so that it gets extracted and written into this directory. And then you're going to have to make sure to get the library before it gets deleted. So like there are a couple of ways to do so. You can either patch the PP compiler, which is responsible for creating that directory and doing all this work, like meaning responsible for extracting the libraries and deleting them right after creation. However, this is definitely not a sustainable approach, and we'd have to do it every time a new release of the compiler is released and on every platform. And you're going to have to write a code that would trigger every single library. So this is definitely not a good idea to do. Thus, why we need to automate this entire process by writing an actual parser that parses those proprietary file formats and extract the library statically for all platforms and all versions of the compiler. So now comes the crust of the talk, actually. This is where we talk about the dissection of these proprietary file formats. So on this slide, I know it might be a bit overwhelming. There's lots of information here, and it is in a small font. However, we'll go through it step by step. And we'll start from the left. So first you will see those 47 hex bytes. So those are extracted from the beginning of the library known as alpha image. And we will reverse engineer those bytes without doing any actual reverse engineering, actually. We will go through them byte by byte and figure out what they mean. So first we'll go through the number one structure, which what I name the PP lib header. So we'll start with the first couple of bytes. So the first 4 bytes, they have this ERUP string, which is stored in little endian, and which, since we're talking about PureBasic, you can clearly tell that it is pure and reverse. So I take this as a magic value and set it to this data number. And then followed by this double word value, which is actually, which indicates the starting offset of the library data starting from index 0C. So how did I figure that out? Of course, you will see later on how. But when reversing binary formats like this, you're going to have to look at the bigger picture, not at the first couple of bytes. And then the third data member has this value, again, in little endian for Bill. So this indicates the library version, and it could take either of the values, lib3 or lib4. Like this is based on me going through multiple versions of the compiler. And then followed by this double word value that is in blue. So this data member takes either of the values 0 or 1. If it is 0, this means the library is stored non-compressed. If it is 1, it means it's stored zlib compressed. And then what follows is another double word value, which is here, indicates the size of the library file decompressed. And again, this is in Little Endian. So LE stands for Little Endian here. And then what follows is the original name of the library. It could be stored on a different name on disk, but this is the original name of the library. And you can tell that it is a null terminated string, and this is how I know it is the end of the name. So this is the first structure. This is easy to parse. Now comes what I call the PB-lib type. So it turns out that the author make a distinction between two library types, which I ended up calling them library type 1 and library type 2. So first we'll start with the PB-lib type, the parent structure for type 1 and type 2 structures. So right after the original file name of the library, we have this byte 01. This is always fixed, and this is what I call the library type, as follows here. Then followed by this byte in dark yellow, 00. Now here, this is where it gets interesting, because it is the value of this byte that decides whether we are dealing with a library of type 1 or a library of type 2. So as per this comment here, if any value other than 00, if the byte at this offset is any value other than 00, the value represents the number of referenced PureBasic system libraries that follows. And I will mention later on what are those system libraries. So if it is 00, it means we're dealing with a library of type 1. And the byte that follows has to be set to 2. It's fixed. It's always 2, meaning it is this data member, library type const. If the value of the data member at this dark yellow is not 0, it means we're dealing with a library of type 2. And then I have in this structure what I call shadow members. These aren't members of the actual structure itself. They just help me when parsing these structures. And here we talk about number 3. We reference library of type 1. And it has the following structure. So just note that this particular example is actually of type 1. Oh, sorry. As you can see here, so the first data member of this library is the class name. And as you can tell, it is this one in blue. It's in light blue, followed by the null terminating character 0. The class name is actually like when you want to use code, sorry, inside alpha image library. So it is stored, all the code is belongs to the class called image. How do I know that? It is, of course, you can go through the documentation that comes with the compiler and figure these things out and make sense out of it. So it doesn't come like to you like this. And then the byte that follows this here, 01, actually indicates what I call the number of referenced internal libraries. In this case, it is 1, so we have 1 referenced internal library. And in this case, it is the name is image, as shown here in gray. So you would expect that this alpha image library referencing another library under the name image, which is also another proprietary library. So this is library type 1. For library type 2, it has this structure. So remember, I said if the value of the number of reference system library in the PB-lib type structure is anything other than 0, it means it indicates the reference of what I call system libraries. So in this case, this data member here, the vector of type string, would hold all the reference system libraries. So on Windows, for example, these would be, for example, OLE 32, add API 32 libraries, and whatnot. On Linux and macOS, they would be different, of course. So those are the system libraries that I'm talking about. So that meaning that this particular library references those system libraries as well. And then this is followed by, once you parse all those reference system libraries names, this is followed by the library type, which is also fixed to 02, and then followed by the library type name, and followed by number of reference internal libraries, the same as in type 1 library, and of course by the list, followed by the list of those internal libraries. So I hope this is clear. I know it's a bit overwhelming, but if you go through the entire process step by step, you will figure it out. Now, remember I mentioned that those libraries, they are stored zlib compressed, yes or no, on Windows, whereas on macOS, they are stored only encrypted and not compressed in any form or shape. And of course, you can tell by now that those libraries, they aren't meant to be used/abused by anybody else. And actually, the author clearly mentioned in the documentation that no one is allowed to use those libraries in their own code, because he invested all this time in writing those libraries. You can clearly use them in your code should you choose to, but definitely this is against the rules. On Linux and macOS, the member, as per the previous structures, the zlib compressed is always set to 0, of course, since they are not compressed. Instead, at this particular offset, we see this value. So the size of the decompressed library is actually this particular data member is set to the library version instead. And actually, this is how I decide if I am parsing Windows or macOS and Linux libraries. It is by checking for this assignment. Initially, when I wrote the parser, I left it to the user to decide whether I am parsing Windows or macOS Linux type library. But it turns out to be much easier to auto-detect such difference. So here we talk about the other part of the header of the proprietary file format. Here we start from where we left off, exactly at the specific byte. Interestingly, the header of those libraries actually include list of all referenced APIs in the library itself with some metadata information specific to it, including the API name, number of arguments it takes, and the size of each of the arguments, and another double word that indicates the API type, and then a help that tells us, like a help message that gives us information about what this particular API does. And this is illustrated in this structure, what I call PB function declaration list. So starting here at this offset, 45 byte, so you can see that this alpha image library has this API called end alpha image. Okay, so this would be the API name, and then the next data member holds the number of arguments that this API takes. And in this case, it is in blue and 0, meaning that this API end alpha image takes no arguments. And then what should follow is the argument list. But in this case, again, this API takes no arguments, so you'd expect to see no argument list. And indeed, it is set to 0. And then what follows is the API type. And this is double word value. It is it is in green. Uh, uh, this value actually has no relevance when reverse engineering those libraries, and it changes per API and even per library. And I honestly couldn't figure out what it means exactly, and I'm not sure what does the compiler do with this particular value. I'm not sure if it's just meant for tracking purposes, like when these APIs gets updated between releases. I just don't know. And then what follows is what you should expect to see is the help of this particular API. And in this case, the value is 0, meaning it comes with no help. Of course, it will not be the case for other APIs. And also, as you can see here, we have another API referenced in this library, or exists in this library, I should say. It's init alpha image, followed by the same structure. So yeah, so this is the function declaration structure. And of course, you could have, I don't know, hundreds of these APIs, I should say functions, with all this metadata according to the structure. And here you can tell the difficulty of parsing these data members, or this structure, I should say, because there is no value that indicates the size of this structure. So you'd have to be very diligent in parsing it so that you don't step into other structures. And we come to number 2 structure. And this is the most important one, actually. This is the one that holds the information that allows us to extract the actual library in its original format. So again, this starts with the magic value, pure, stored in little endian. Here you can see it here, Europe. So we have this value here. It is an orange, and then followed by this double word value, which holds the length of the library, actually, as it's stored in this proprietary file format library. So when parsing, you want to extract the library from this library file. This is how much you have to read. And then followed by the type of the library we're dealing with. So again, it's a little endian. In this case, it is .1. It is of type .1. It could be a debug library. And then followed by the actual library data. Could be zlib compressed or non-zlib compressed. And here you can see me highlighting those first 2 bytes of the library. They are which holds the values 789C. This is actually the header for zlib compressed data. And this is how I know that actually I'm dealing with zlib compressed data without doing an actual reversing on the compiler. And again, I have here this shadow member called isDebug build. So this actually would be set to true in case the type is debug 1 or not. This just to help me when parsing the library. So yeah, now moving into step number 3. As I mentioned, on macOS and Linux, those libraries, they are stored encrypted. And after looking at a couple of versions, they all have the same decryption algorithm with this static key, and it's the same key for all versions that I looked at. And the decryption is actually quite simple, not sophisticated at all. But you can tell, sort of like gives you the idea that the author doesn't want you to look into these libraries because he invested all this time into them. So, so yeah, first you take, you read 4 bytes at a time from this encrypted data, and then you subtract them from the key, followed by, like on every iteration, you add the file size to the key, and then you get the decrypted data, and then you keep looping until you finish parsing the entire library file. It's quite simple. And here the file size, it comes from this data member. If you go back here, and sorry, file size. Oh no, it's here actually. I don't know why I went there. It is this one. It's this data member. It's the pblib data length. It's the size of the library. So yeah, so that's that for actually parsing the actual header of those proprietary file formats. Now there is another file which holds the actual resident files, and it has its own structure too. But I don't provide a parser for those because I just don't see the importance of that. And this is the actual structure of those files. Now, just to keep in mind, do not confuse resident file for resource files. So resource files, they are meant to store strings, a GUI, typed elements, and whatnot. Resident files, these are proprietary to the PureBasic compiler. And as I mentioned, they store structures, classes, and constants in binary formats. So in this structure, you can see it outlining how these types are stored inside the resident files. So it has this structure. I believe it's quite simple. So you might be wondering, how did I know that, for example, prot, like when I see this marker, how did I know that it's holding interfaces, meaning class type information? I mean, it's a trial and error. You sort of go through the library when you open it in a hex editor, and you start wondering, try to make sense out of this data. And this is how you start labeling stuff until things start to make sense to you. So, but parsing these files should be quite easy. It's not a big deal at all. I just don't see the point of providing a parser for it. Now, a couple of notes for those who are interested in doing reverse engineering proprietary file format without doing any actual reverse engineering type work. First, you're gonna have to familiarize yourself with the framework that you are researching. Like, you have to read about it as much as you can, check the documentation, take notes, run this, run that, play with every directory, execute this file, execute that file, watch what happens on the system, play with it, write code, and whenever you're in doubt, of course, Google for additional information. Perhaps somebody else talked about the same thing. So yeah, and of course, it goes without saying that the most important tool when you want to reverse proprietary file format, especially in binary format, is a hex editor. Like, this is probably the most important tool, and you're gonna have to be very well accustomed with the usage of the tool itself. And of course, experience does indeed play a major role, especially when you want to identify or sort of spot particular patterns or specific constructs. So the more experience you have, the easier it is to spot such interesting patterns. Otherwise, it's going to be a bit more difficult and more time-consuming. That's for sure. And another note when reversing binary formats is you're going to have to look at the bigger picture. So you can't just pick the first 1 byte, 4 byte, or the fixed 16 byte, depending on the structure of the file that you're reversing, and the size as well. So it's better if you take first a closer look and you step back and you take another holistic look at the entire file. And you have to keep in mind certain things. So for example, you look at 1 byte type, size-wise, a word type size, a double word type size, and of course for strings that's terminated with the null character. And you got to look for repeating patterns, which would give you telltale signs about the nature of the data that you're dealing with or what should follow as well. And yeah, the other thing is that you're going to have to look at multiple files of the same format. And searching for any differences that might emerge out of this endeavor. And again, I mean, reversing binary format is more complicated and more sophisticated than reversing a text-based format. So reversing an INI files is nothing compared to binary format, especially when you want to make sense out of everything that has no contextual representation. So after extracting all those libraries and everything, now comes the time to demo the work that I did. So as I mentioned that I wrote a parser that would do all the work that I talked about, right? So the parser is written in C++. You could actually use other tools as well. For example, if you don't want to implement your own parser, you could use a library known as the name Blobify. It's a C++ 17 header library, and it gives you the option to serialize, deserialize data. But again, it's definitely not going to handle all the intricacies of this particular file format, so you're going to have to do lots of work on your own, actually. Or, on the other hand, you could use a Kaitai framework. It has its own abstract language, just YAML file with its own specification that would generate the actual code that would do the actual parsing for you. But again, there is a learning curve, and I'm not sure actually if it's up to the task to do the actual parsing of this file format. But at the end of the day, it's better if you write your own parser just as a learning experience. And so this this parser is actually parses all the compiler platforms, libraries, and it prints all the structure that I talked about in a very contextual format. That's all with all the offsets, and of course, it extracts the actual COF file format in its original form to disk for all compiler platforms. And the list of function declarations, you could also save them in an XML file should you want to consume them in one way or another. And so to demonstrate the parser, I'm gonna go through this now. So I took the library called Gadget as an example, just to demo it. So first you invoke the parser as follows. So you give it the name of the library that you're interested in, Gadget, and you want to print to the console those structures. So -p is the option. And oh, sorry, it is F for the library name. And here it prints everything for you. Okay, so if you go to the beginning, so you can see here first the pplib header structure that we talked about first, the magic value, which holds the value, the magic value, a member holds the value EREP, and the index into the library data at, if you remember, at offset 0C, it holds this value, library version. Is this library compressed or not? As you can tell here, it is 1, meaning it is 0 compressed, and the size of the library decompressed, and the original file name, and this is the shadow member. And you see here the offset is set to -1 because it's not a part of the actual structure or nor the file itself. And then followed by followed by the other structures. So in this particular example, like the gadget library, this is actually of type 2. So it should be outlined here. This is it is library type 1. I said type 2. Type 1. No, it's actually type 2. Sorry. Library type. Oh, sorry. This is a byte value. Never mind. And so this library is of type 2. And I want to show. So yeah, I just want to mention this. If you remember, I talked about the list of reference system libraries. So in this particular example, you can tell this is the library names. So these are Windows specific libraries that resides inside the Windows directory that function as a proxy into Windows APIs. And the list goes on. And this is where you see the list of all the function or APIs in this library. So you can see here it has the structure for the API name, add gadget column, followed by the number of arguments that this API takes. It's 4. And the size of each of those arguments. I know here you might be wondering, how can we have a value of size 4? Of course, you can look up the documentation of this API and then you can figure it out. And then this is the value, the integrating value that I couldn't figure out what it means exactly, this double word value. And as you can tell, it changes for a different API, but not for every single API. As you can tell here, it's the same. And this is the help that tells you what this API is supposed to do. And in this case, the first one, it adds a column to the specified gadget. So yeah, and the list goes on, everything. So the other option is the extraction of the library itself. So you give it the option E and extract the library to disk. Here it saved it under the gadget.lib. So if we go and open that library, so you see here it saved it to .lib. So if we open it, you can see the actual COF file format of the library. So you can see it here. Also, again, as I mentioned, you can dump all the list of function declarations to an XML file via this argument. And again, it saved it with this XML file. Just to give you a look. And this is how it looks like. So I believe this is would be important for people who want to consume this information, like some other tools or whatnot. Okay, and that's the whole parser. Now, again, the most important part after doing all this work is that we want to help reverse engineers reversing PureBasic binaries. And to do so, we're going to have to generate IDA FLIRT signature for it. So the generation of the FLIRT signature is not sophisticated, but I also, on top of it, I wrote a simple IDA plugin that allows you to identify first that the binary that's trying to reverse it is PureBasic binary or not, and then it will auto-apply IDA FLIRT signature for you to annotate all the reference PureBasic APIs in the code for you. And of course, it deals with 32 or 64-bit executables and apply the signatures appropriately. And how the plugins identify that it's dealing with PureBasic binary or not? It simply checks for the prologue of the PureBasic binaries. And of course, it has the capability to look up the documentation of a given API, either online or in a CHM file, which is just another help file format for Windows. You can simply copy this file to the directory of the plugin from the PureBasic installation directory, and it will work just fine. And here I just sort of document the prologue of some of the PureBasic binaries. For example, for 32-bit exe files, it has this prologue, like literally this very same prologue down to the constant. And this is actually how the plugin checks for it, like exactly as shown here with the opcodes and the bytes. Here I literally check for the 6.8, followed by the wildcards, and followed by 0, 0, and whatnot all the way. And for checking for 32-bit DLLs, this is another prologue. And this is another PureLock pattern for checking 64-bit PureBasic compiled binaries on Windows. This works for both exe and DLL, surprisingly. They have the same prologue. I don't know why. I don't know why it's not the case for the 32-bit version. So if you're curious, actually, about these assembly instructions, so if you reverse engineer pb-compile.exe, you will see it actually emitting those assembly instructions to the PureBasic.asm file. They are stored as it is, so you can verify that yourself. So before demoing the plugin, let me first talk about the generation of those IDA FLIRT signatures. So IDA comes with its own SDK, and it is no surprise that you won't have access to SDK unless you have a paid version of IDA. It's this SDK that has all the tools necessary to generate those FLIRT signature. So the instruction in this case, they are specific to Windows, to the Windows version. However, it's pretty much the same for all other platforms, since the SDK comes with all the other tools for all the other platforms. So once we acquire all those libraries that we extracted, so we need to generate the FLIRT signatures again. FLIRT signatures, I mean, it's a very well-known technology for IDA. Just to give like a brief introduction, it's a function and library identification and recognition technology by IDA. So it's responsible for parsing all those libraries and generating what's known as pattern file. So once you generate the pattern file, then you can generate the actual signature file that would be consumed by IDA, so that it labels all those PureBasic functions in the binary with their respective original names. So first you use the tool pcf.exe to generate the pattern file against a given library, and then use the sigmake.exe tool to generate the actual signature file. Now this goes without saying that you might encounter during this process some collisions, meaning that you might have two functions inside the library that would collide with each other in terms of pattern matching. In this case, it wasn't a big deal because most of the collisions happen with what's known as debug functions. So those technically aren't really that important, and they are very small. So no wonder they ended up colliding with each other. So those I could easily fix. And the plugins ships with 4 major signature files, targeting the latest version of PureBasic. At the time when I did this research, it was 5.71. I believe now you have version 5.72, so it's still a minor version. And the signatures, I ship both for 32 and 64-bit builds. So yeah. And in case you're wondering about those pattern files, actually IDA does come with extensive documentation about the specifics. So this is an example. This is the PureLocker ransomware that was first documented by Teaser. It is written in the PureBasic language. It's actually unknown what version of the compiler was used to build it. However, we know that it uses custom functions, anti-analysis, and since it is a ransomware, it actually uses PureBasic based encryption functions. So first, when you open this binary in IDA actually only recognize 18 out of the 231 functions. So you're left out with more than 200 functions to reverse engineer by yourself and label and whatnot. However, after applying the PureBasic signatures that we generated, IDA recognizes 124 out of 237 functions. So life becomes easier when reversing this binary. And to note, you can see here that IDA actually sort of discovered new additional functions after applying the signature. Yeah. So to give you an example how it looks like after applying the signature files, this is how it looks like, and you can tell. So pb_, like the PureBasic names, they have this syntax, pb underscore followed by the API name / function name, and followed by the number of arguments it takes, which is interesting. It's actually good. It's sort of like already telling you just by reading the function name how many arguments this particular function takes. And this is not the case for every function. I don't know why. And here you can see it also labeling the other encryption functions, encryption/decryption functions. Actually, we can demo this first. I already have it loaded in IDA here. So this is after opening PureLogger, the ransomware, and you can see here we have 1 out of 231 functions. You can see nothing is labeled. So we can invoke the plugin on this one via this menu, PureBasic helper. First, we ask it if it is a PureBasic or not via this option, and it tells us, yes, it is PureBasic binary file. Do you want to apply those FLIRT signatures or not? Let's say yes, and gives you this dialog box. So here, by default, you have the first two selected. And I mean, you can select the other two too, but if you know that you're not dealing with DirectX or OpenGL type code, so there's no need to select them. But it doesn't hurt to select them either way. So you can select them and press apply. And then it's going to annotate all the relevant functions. So if you go back to the function window, you can see it here labeling most of those important functions for us, and region dial, CBC, decrypt, encrypt. So if we go to the code, you can see it here. And if you want to see where it's referenced in the code, we can see it here. Again, you see it here. It's AES decoder. Back again, you see it. So this is, it's much better to read this code rather than having to read non-annotated code. So yeah, so it does work. So going back to the slides. So this is another example. I just pulled this example actually from the examples directory from PureBasic installation folder. It is just responsible for actually loading XML files on disk, parsing it, and displaying it in a GUI type window. So after compiling this file and on Windows again, and loading it in IDA, you can see that IDA only identified 41 out of 559 functions. After applying PureBasic signatures, IDA identified 300 out of 585 functions. And again, the same thing happened here. IDA discovered an additional 24 functions after applying the signature, of course. Actually, since you might be still wondering, we're still left with 285 functions that haven't been identified. Those functions are actually not relevant at all, not important to the core functionality of the example itself, actually. And you can look it up yourself. So this is the contrast between the two. Originally, this is how the code looks like. So after compiling the XML example, as you can tell, all the function calls, they have no names. So it's definitely harder to reverse engineer. After flirting that example, meaning applying the FLIRT signatures, as you can see here, pb init XML, this code, this is what it does. Then we have the open file requester. It's going to open a window asking us to select the XML file on disk that we want to open, /parse. And you have this code that loads the XML, and the list goes on. You probably want to see it in action too. So again, I loaded this file already in IDA, and as you can see, none of the calls are labeled. And if you go to the list of functions, it's the same here. So again, we do the same thing here. PureBasic helper is the PB binary file. It says yes. So we say yes, and we apply with all the signatures, and voila. So just to make it look nicer, you can the demingle name set and the demingle set of comments. And as you can see here, we have open file requester, you have all the initializations, load XML file, the status of the XML file, and all the other PureBasic specific function names. So yeah, it is as simple as that. So actually, another note to keep in mind, if you're suspecting that you're dealing with a PureBasic file, but this option is not detecting the file as PureBasic, you can still sort of apply the PureBasic signature by clicking here and force the applying of those FLIRT signatures. Of course, you can do it the other way by going to View, Open Side View, and the Signatures window, and doing it from there. And the other thing, as I mentioned, that is, you can actually look up the documentation of a specific API. So if it is from CHM file, we'll see, it takes us straight to the documentation of this API here. And of course, you can do the same thing, but online. It's going to take you to the default browser on your system, pointing to this API on the compiler website. So yeah, back to the slides. Now here, some challenges. Well, that might not be challenges for you, but they were challenges for me, and recommendations and some future work. The thing that I found the most difficult is collecting all versions of PB compiler so that I can write FLIRT signature for all the versions, because of course there will be differences where the identification of some of the functions fail due to major differences in the code. We need not account for all the versions, like every minor release of the compiler, as much as only the major releases. At least, like now we're at version 5, we need version 4, version 3, version 2, or something in between as well. So that's that. And then this, if we get all these releases, then it would create sort of like a knowledge base for all the compilers, libraries. What is left as well is generating FLIRT signature for the other version of the compiler libraries. I mean, this is quite easy since I already wrote the parser, so it's just a matter of somebody doing this process. Actually, the demo version of the compiler comes with all the libraries, so this is not about having to pay for the compiler to generate those signatures, just that somebody has to do it now. And yeah, and probably at some point in time, writing a parser for those resident files, although I don't see the point of that. And some additional update to the plugin is not, doesn't hurt actually, to actually consume those XML file and label all relevant function in IDA with the metadata of each of the functions. And probably add support for detecting PureBasic files for Linux and macOS. And for some of the functions that the FLIRT technology is missing, especially the sigmake because of collisions or whatnot, for whatever other reason, probably we can generate a unique set of FLIRT or signature files like manually using the IDA2PUT plugin. Another thing that you probably need to be aware of, and this is more of a lesson learned type thing, especially when you want to write your own parser. Because if you still remember by this point of time, some of the structure they are very dynamic, and they have different offsets, and then some of the data doesn't have a member that would indicate the size of this data. So parsing becomes actually quite difficult, and it might not be difficult for you, but it was challenging for me. And in this case, I have actually one recommendation. That is, if you know beforehand, you should actually, since you must have done a good amount of understanding of the file format, you copy each block of the structure separately actually, and parses it separately, so that you don't end up stepping into other structures when parsing it in your code, and you don't have to keep track of all the offsets as well. especially if you have a set of global offset that you have to update to know where to start parsing, what this byte means now, and you have lots of ifs in your code or whatnot. Just if you know the structure already, you know the size of it, you know its delimiters, just copy it into a separate buffer and parse it as a standalone structure. So yeah. In conclusion, I usually actually don't give conclusion. I leave it to the audience to make up their own conclusion, see if they understand the presentation or not. And just one thing, a lot of people, they just get confused. That is, again, remember, you have to read the abstract before going through the slides. And in case you're wondering, yes, I'll be releasing the parser, the IDA plugin, and the FLIRT signature on my website, mfmokbel.com, of course. And that's it. And if you have any questions, please ask. Thank you. Bye.